Okay, so this is an Adam simulation of not a serial robot, but a parallel robot. It's like a wheeled vehicle. So you can do fancy things like this. That is all I'm trying to impress you with. Okay, so basically what this is a robot. This is the work of a PhD student. So you have this wheel, you have this 3-wheel robot, then there is a body here, and then they are connected by links. If anybody is interested, you can see this. And then there are these 3 motors, each for 2 wheels and 1 wheel, front wheel for steering. Okay, and this robot is going over an uneven terrain. It is not on flat ground. Okay, so you can make a set of differential equations for this. It is possible. So you will end up with some 24 differential equations. Okay, 24 second order differential equations, because there are lots of variables. Okay, so there is a variable here, then there is a variable, the wheel is rolling, the wheel is tilting, then there is a variable for this platform X, Y, Z. So lots of variables are there. Eventually you will end up with some 24 differential equations which you need to solve. But instead of doing that, what you can do is, nowadays there are these very powerful tools which are available. You can create a model in Atoms. Okay, you can create a model, CAD model of this wheel. You can create a CAD model of the suspension. There is a 2 degree of freedom suspension also involved. Then there is a platform which is own mass, inertia, everything is there. And then you need to provide constraints that I want to make sure that this wheel is always on top of the ground. It is always touching the ground. Okay, you need to put in some value of friction, and then you let it simulate. So you give some motor torques and see what the robot does. In this case, the wheel mobile robot does. Okay, and you can see that you will get such nice, realistic simulations which are possible. So you can see that there is a model of a suspension like a steering, and then this robot is going over uneven terrain. So it will make sure that it will tilt back and forth as that it goes. Okay. So this is the work of a PhD student about 3-4 years back. He showed how you can model these wheel mobile robots. Again, equations of motion. He did it using Lagrangian only, okay, and showed that similar things you can also do with in Atoms. This is another robot which is, again I just want to show some video, and again it's not possible to derive and explain each and everything, how the equations of motion were derived, how the control was derived, but I just want to show you that exactly the same idea. Again, you find kinetic energy, potential energy, do everything exactly the same way. So this is another robot which has this 1, 2, 3, 4, 5, 6, 7, 8 links. Actually, each link is like a motor. Okay, and what the motor is doing is it will rotate. So I want the tip of the robot to trace a path. In this case, it will be a circle. Okay, so I want to make sure that I have chosen the right motors. Okay, how I want to move it in a path such that it traces a circle, similar to that simple 2 degree of freedom which I showed you. Okay, but in this case there are many more joints. I have to figure out what motors to put where. And later on tomorrow I will discuss control, how much to move each motor such that it goes in a circle. Okay, so in order to do control, before you can do control, you have to do dynamics. You have to simulate the motion, you have to figure out what the robot is doing when you are applying some tasks, such that later on you can go and do control. Okay. Okay, I don't have the same dynamics equation of motion. You can also do simulations like this. This is for a 4-bar mechanism. Okay. So suppose the 4-bar is lying straight and you apply some torque here. How much time does it take to move? You can find out all those things. So dynamics is essential to do. This is a simulation example for a 4-bar, for a parallel robot, for a 4-bar mechanism. Okay, so I can find out how much time it takes. Okay, so I finished a little early, so I thought you can ask some questions if anybody is interested or interested. There are many other videos if anybody is interested of where dynamics is very essential.
Closed form equations in Adams?
No. Adams does not give you closed form equations. Adams will only give you the output. You can plot what it is doing. You can even find out forces, numbers, but not symbolic equations. Any other question? There is a lot of material. I thought I will not give you too much detail, but here is another video. No, sorry. Sorry. Anyway, there are many cases which you can show. Yeah. Okay, so here is a video of another robot which again you need to do so this is also another robot which another student has worked on. So again, dynamics is involved, control is involved, and also in this case we want the robot to move in this field, okay, such that it is also avoiding the obstacles. So again, I need to know how much torque to apply at each joint given a certain path. Okay, so this is a robot which is similar to that one which I showed you. This has many more links, 12 links. So there is a motor which is at the front, which is driving the wheels. And the goal of this exercise was, so not only dynamics, but extend it to what is called as obstacle avoidance. Okay, so again, we can apply, we have to compute the torques such that it will not go and hit anything. Okay. So once you find out the dynamics, once you make sure that your algorithms are working, you need to send it through that wire, how much voltage, how much current you need to apply to get the required torques. Okay, and that is what it is doing. So that is the next step. Any other question? Yeah.
The term Coriolis acceleration generally introduced as when we observe the motion from a rotating reference frame. Typical example, which is say the drag and slaughter layer mechanism, like that. So here, how the term comes over here, the term is used here.
No, the term will come. See. So if you were to, so this example everybody can even work out by hand and they can see what exactly is happening, okay. Other times it is very hard. So when you compute the kinetic energy, the kinetic energy is half mv square plus half I omega square, okay, for each link. So when you compute the kinetic energy, you will see some term which is cos theta 2 which will come, okay, and there is a reason for that. So if the link is very far away, you have much more velocity. If it is like this, the inertia is smaller. Okay, so you will get some terms which is C2 here. Okay, then when you take these derivatives, so when you take these derivatives with respect to theta 1 dot, nothing happens. So theta 1 dot, that is, it is. So here you can see it is related to theta 1 dot square, theta 2 dot square, and so on. So there is no product term theta 1 dot into theta 2 dot yet. Okay, so kinetic energy is only theta 1 dot square, theta 2 dot square, but there is a term which is C2 into theta 1 dot into like this will come. Okay, this term is there. So when you take the derivatives with respect to time d by dt of this, then you will see, you will get some theta 2 dot into 2 theta 1 dot, theta 2 dot into theta 2 dot square. Okay, so these are the centripetal and Coriolis terms. There's nothing you can do about it, it will always happen. And this is with respect to the kinetic energy is a scalar, it doesn't matter with which coordinate system you are, whether rotating frame or non-rotating frame, it doesn't matter. Okay, it's a scalar. It's like so many joules of energy. Okay, so energy does not matter whether it is with respect to rotating or some other coordinate system. It's a number. Okay, it's a scalar. So when you take the derivatives, which is what Lagrangian formulation tells you to do, you will get terms like this. Okay.
So the MATLAB simulation you have shown, It's a pure robot just happening free fall. So if you were to introduce a damping into that, which formulation you use?
Yeah, if you were to include damping, then you will see eventually it will come down and be vertical.
So which modeling you will introduce? Can we do the Lagrangian and introduce the damping?
Yes. So as I said, the problem with Lagrangian formulation is this term is not there. There is no friction term in the Lagrangian formulation. Okay, it doesn't appear. It is not taken into account. It is for technically it is for conservative systems. So if you want to include friction, then so in this equation of motion for the 2 degree of freedom here. Okay, so this doesn't include friction. So what I have to do here is I have to add one C1 into theta 1 dot plus C2, some constant, and here into some C2 into theta 2 dot plus some constant. Okay, and what is the value of the damping coefficient? That is up to you to choose. So here there is and that is also a very important thing to recognize. The Coriolis and centripetal term have theta 1 dot into theta 2 dot squared and so on. Okay, but they are not friction, they are squared. Okay, the Coriolis and centripetal terms have theta 1 dot squared. So you can prove that this term, the Coriolis term, does not contribute to the energy of the system. Kinetic energy is there, which is giving this. Potential energy is there. So where did this come from? That comes from the fact that you take all these derivatives. So it does not contain viscous friction. This is not viscous friction. This is centripetal and Coriolis term.
So also if you want to add a flexibility component, till you said Lagrangian you cannot use.
You have to model. If you want to include flexibility, one simple way of including flexibility is to modify this potential energy. So if you want to, let's say that there is a spring, one very crude model of modeling flexibility is to say the joint has a spring, okay, which is some half k into theta square. Some energy is stored in the spring. Then you have to add in the potential energy, but that is very crude. So if you want to model the flexibility of the beam, so there is this whole theory of called Euler-Bernoulli beam, okay? So where you have some I, fourth derivative of some displacement is equal to something. If you want to go to that kind of model, then this can't be used.
Sir, for a model-based control of articulated movement, real-time computing is a big task.
Yes.
So, is there any other way of doing for this kind of dynamics and kinematics for?
So that is the whole reason why I told you that we need very efficient computation of inverse dynamics. So tomorrow I will show you that in model-based control you need to do only inverse dynamics. You don't need to do the simulation. Okay. So for example, that robot which was going through these obstacles, all it requires is you know the path, because that is the path. That is the obstacle avoidance path does not come from that is up to you to decide. Okay. For that path, you need to know how much torque to be applied at each motors. Okay, so you need to solve only the inverse dynamics. You don't need to solve ODEs. You don't need to use MATLAB. You just need to substitute on the right hand side of the equations of motion whatever is the path variables and as a function of time. And so as I said, important thing is to do it in very efficient way. And the most efficient way, or one of the most efficient way, is using this ON, linear complexity. So if you have linear complexity, if you have large number of links of the robot, even then nowadays computers are fast enough to compute the right hand side. So just substitute. So substitution means what? You have to say theta dot is 2, theta is 5, whatever, some numbers, and you have to just calculate this right hand side. So in model-based control, all you need to do is you have to put what is I1, I2, MR squared. So you have to do multiplication and addition. That's all. Okay, and maybe some sine theta 2 you have to do. That's the most complicated thing that you have to do. Okay, and that can be done nowadays with enough, computing resources are available to do that very quickly. And the robot was not moving very slowly. You could see it was not moving very fast. Okay, so typically again in control, you need to move. There is this: how much sampling are you going to do? How fast you want the robot to move? Okay, so most computers nowadays are available which can do this right-hand side computation within some few milliseconds, and hence it is okay.
So this obstacle avoidance problem, whether this robot is able to identify the path, estimate the path?
That is your, in that example which I showed you, the path has been found out by some other algorithms, not real time. So the path was known, that the head has to move in this path.
Predicted by the designer? No?
Yeah, it is not by design, by another algorithm. Yeah.
Estimating.
Yes. So, I mean, in IISc we don't have so much resources, but these kind of things can be also done by using a sensor. So if you have some sensor at the end of the robot which can see that these are the obstacles, then it can real time change the path. Okay, but we can do that.
The Coriolis force is not adding towards the energy consumption.
Yes.
So actually, is it a vibration happening to that? What is actually the contribution?
Where is it coming from?
What it contributes to? Coriolis
No, it contributes, it is just changing. This is the term, it does not contribute to the total energy, but it shifts. I mean, this is a very crude way of explaining. It shifts between kinetic and potential energy. As the thing is moving, okay, so initially it is kinetic energy, then it is potential, some changing of energies are happening, okay, and because of that change, these terms will come. So if it is like, in your, what is the other example of Coriolis, centripetal force? Yeah, you take a string and you rotate this. Okay, so as long as it is rotating, there is no change in energy. Okay, but the direction of the velocity vector is constantly changing as it is going, and that shows up as centripetal force. Here they will also have, so these terms are called centripetal, theta dot square, and if you have theta 1 dot into theta 2 dot, that is called Coriolis. So if you go back and remember, it is some 2 omega cross v. Okay, one of the term in an acceleration is omega square r, and the other term is 2 omega cross v. So that 2 is also here. Any other question?
Sir,
Yeah.
from the dynamic model, state space model, can you identify the motion is quasi-static or completely dynamic?
Quasi-static?
Quasi-static is slowly moving, or it is moving fast. Then this dynamic model is very important. So it is moving very slowly or...
Yeah. Okay, so if I understand your question, okay, there is a lot of interest or lot of interest, as you said, to know when do we need to use dynamics. Okay, so if you look at the equation of motion, as I said, for any robot, there are these terms. Okay, so one is which is mass into q double dot. So this is like torque equals I alpha. Okay, so this is like generalized form of I. Okay, when you write rotating things, you have I into alpha. This is the Coriolis term, this is gravity term, and this is friction term. So if, and you can find out this. So once you do the simulation, you can calculate how much is this term. Okay, how much is this term? How much is this term and how much is this term? So one way of saying when dynamics is important, when this is important. This is comparable to the, let's say, the gravity term, or comparable to the friction. So if your inertia term, which is this term, okay, so suppose you get 5 Newton meter, I'm just giving you a very crude thing. You give 5 Newton meter and you find that this is 2 and this is 1 and this is 1 and this is 1. Okay? So then it is important, no, because this inertia part is 2, comparable to 5, comparable to 1. But it turns out that if it is moving very slowly, q double dot is very small, then most of it will be in gravity and friction. So then you can assume it to be quasi-static.
So the static modeling is.
So statics is this. So you ignore this term, you ignore this term. So you have only friction and you have only gravity. Anything else?
If there is a lateral vibration on the joints in the serial navigator, what happens how can you just model?
You cannot do it this way. As I said, if you have vibration, so vibration basically means some spring is there, some storage of energy other than gravity is happening. Okay, so if you have a beam which is vibrating, okay, then there is a strain energy or there is some storage of energy which is being stored. So that if you want to include, as I said, beam vibration, if you think that the robot links are as beams which are vibrating, then you can't use this. One crude way which many people did for a long time was that there is always some spring or some vibration at the joint. Okay, so if the robot is moving fast, there is some gears are there, gears are meshing, some vibration is there. So for that, you can include one's half kx square, half k theta square, like a torsional spring. But for the beam, you can't do this. Any other question? Okay, thank you. If you want, if these notes are there, you can read this. So I skipped a lot of things about that, but four bar and parallel, because I think Dr. Ghosal, they will probably talk about these also. And there are all materially repeated also. And there is a book also which I have written, so you can buy that book also. Thank you.
Tomorrow's session will begin at 8 o'clock. Sir has to go immediately after that session. So we cannot delay. Start at 8 o'clock.